Thanks for coming to the last session of the day. So the first speaker is going to be Idan.
Yeah, thank you. Okay, so I will tell you, can you hear me well, by the way? Am I screaming? Okay. So I will tell you today about computational hardness of learning regular expressions. This is a joint work with Lev in the audience. This is Nati with my daughter about a year ago. This is my daughter a few weeks ago, and Gal. So let me tell you about the result in one slide. Let's say we want to learn a regular expression for a spam filtering task. So we have these wonderful messages. You've won a cash, you're come to the casino, and so on. And let's say it's generated by a regular expression. So this is our target function. And we want to output a classifier that approximates this regular expression, meaning it answers the messages that generated by this regular expression similar to the regular expression. Okay. So what are the results? It's hard to learn regular expressions improperly in the PAC setting, even if we allow membership queries, which is not the case with deterministic finite automata, because there is an efficient algorithm for that. So the same regular language has different representations, and it affects the computational complexity of the problem. PAC learning, even with respect to the uniform distribution, is hard. And the general message is that learning regular expressions is not equivalent to learning automata. Okay, okay, so what is the setup we're working on? In PAC learning, we have an unknown regular language L. We have an unknown distribution D. We can sample from D strings, and then it's labeled by some concept, unknown concept C. This concept indicates the membership in L. It can be an automata. It can be a regular expression. And then we want a learning algorithm that outputs a function H that approximates well the concept C with respect to the distribution D. And H could be any function, meaning we're in improper setting. We're not, we don't need to output a function that this is a regular expression. We can output whatever we want. We also allow membership queries, which is we can actively query any strings we want and gets its label. The standard way to measure tractability is per the length of the string. So for length n, we define the language ln to be strings in the language of size n. We define the distribution dn to be a distribution over strings of length n. We want one single algorithm that runs in time polynomial in n, the accuracy parameter, but most importantly in the representation size of the target concept, such that it approximates well the target concept C. The main point is the representation of C is really, really important because tractability depends on this description length. Okay. Common ways to choose a representation. So let's say we want to learn the language of strings that contain the substring 101. We can, on the left-hand side, choose this deterministic finite automata or just a simple regular expression. We all know that both characterize regular languages, and it makes sense to study both of them in different contexts. The way we measure the length of an automata, it's either the number of states, also even binary strings that describe the automata, it's going to be the number of states, log number of the states. Either way, it's polynomially related. And the way we measure the size of the regular expression is just the number of symbols. Okay, so this is the description length of the target concept. There is a long history of learning automata and regular languages, starting from Gold, even before PAC learning, where Gold showed that it's hard to identify regular languages in the limit if we have only positive examples. Then in '87, a very famous result by Dana Angluin that she showed that there is an algorithm, L star, that allows to learn efficiently DFAs with membership queries. Then in '93, there is a proper hardness result for learning DFAs in the PAC setting. To show improper hardness, Kearns and Valiant use cryptographic assumptions. But the point is that little is known about regular languages, and it's not the same. Okay, so why should we care about regular languages? It's really common pattern language used in practice for text search, for validation, for using lexical analysis of compilers and so on. It's also very simple and human interpretable. Okay, so this is, I think, an interesting aspect of the work. This is not our results, but there are languages where the regular expression can be exponentially smaller than the minimal DFAs. And there are languages where the DFA could be exponentially smaller than the equivalent regular expression. How many of you know this fact, that there is exponential blowup in both directions? Good, okay, matches my statistics. Either way, NFA is always more compact than both of them. But the takeaway is that hardness of learning DFAs does not imply hardness of learning regular expressions. And also efficient learning of DFAs, such as with membership queries, does not imply efficient learning of regular expressions. So it's, in some sense, a different question in terms of computation complexity. So this is our results. Results for DFAs and NFAs are well known. We first show for standard regular expressions with the operators of union, concatenation, and star. We showed that this is hard for some distribution in PAC, hard with respect to the uniform distribution. But I guess the interesting result is that this is still hard with membership queries as opposed to DFAs. We don't know the answer for with queries with respect to the uniform distribution. Then we said, okay, we want to prove hardness also for the uniform distribution. We can show that if we allow the regular expression to have more power with negation or complement. So this is an extended regular expression. Note that the hardness is under cryptographic assumptions and average case complexity assumptions. And there is a good reason for that, because if you want to show improper hardness, it's unlikely that we can use NP hardness assumptions. There is a famous paper that shows that if you want to do it, then the polynomial hierarchy collapses or something like that. So this is necessary to make such an assumptions. Some proof ideas to show hardness for PAC and MQ, we have a reduction from learning DNFs. This is maybe surprisingly known to be hard only in the last 10 years. Nice techniques developed by Danieli and Schwartz, Danieli and Vardi, and Appelboim. So the idea is very simple. We can translate any instance of a DNF to an equivalent regular expression with only a polynomial blowup. So this is a simple proof. To show hardness with respect to the uniform distribution, we should have worked harder. So we prove it directly from an assumption. The assumption we used is the existence of a local pseudo-random generator, which is a well-known assumption in the last about 25 years in cryptography. And the proof goes the way that if we have an efficient learner, even weak learner, for learning regular expressions, then we can distinguish random strings from pseudo-random strings, violating the assumptions of the existence of such a pseudo-random generator. For extended regular expressions, meaning we augment the regular expression with complement and intersection, we can prove it with respect hardness in PAC and MQ with respect to the uniform distribution by a reduction from Boolean formulas. This is a well-known results from the 90s by Kharitonov. The proof idea is also quite simple. We can map any literal to a string of length n, and the operators are defined inductively, and we prove it by a structural induction. Main takeaway and open directions. You want to learn a concept. It may have multiple representations, and it matters which representation you choose. So people should care about that. Some open questions. We showed that regular expressions are harder than DFAs with membership queries. We don't know the relation between regular expressions and NFAs. NFAs are always more compact, but we don't know how to translate it to computational separation. Another nice topic that is connected to modern topic of learning formal languages and neural network architectures is what happens if we represent the regular language with circuits. So this is an active research area about investigating the power of transformers and chain of thought with respect to uniform for formal languages. And another thing we couldn't solve is to show what is the computational hardness of PAC and membership queries of either regular expressions or NFAs with respect to the uniform distribution. So yeah, that's it. Questions?
Okay, so our next presenter is Eren Kizildag from UIUC, and he'll present two papers. The first one is on tensors.
So, Latush, thank you for the introduction. The first talk I'll be giving today will be on the large average subtensor problem that I'll be telling you about ground state algorithms as well as algorithmic barriers. And this talk is joint work with Abhishek, who at the time was a PhD student in UIUC. Now he's at Princeton as a postdoc. So here's the model. Throughout the talk, I'll be considering a random tensor with IID standard normal entries. It's an order P tensor where each mode has dimension capital N. And we fix an integer k, and throughout the talk, you can think k as something that grows with n. This is the regime of interest, and we are concerned with the following algorithmic problem. We want to find in polynomial time a subtensor, order P subtensor of dimension k that has large average entry. So this is corresponding to solving this random optimization problem where each lie encode which coordinates I get to keep along each mode. And the particular focus today will be on the ground state, which is the optimal value of this. What are the polynomial time guarantees, as well as some algorithmic barriers. And everything is average case. And for those of you who are familiar with this line of work, this is going to be an unplanted model. So there is no planted signal whatsoever in this talk. But next talk will have some. So before we move on, a little bit of prior work. The submatrix case actually has a lot of applications, in particular by clustering in applied statistics literature. And it exhibits a feature called statistical computational gap. And this will be both this talk and next talk will have some of these ingredients. So on the one hand, the optimal value, which you can pin using non-constructive techniques, is some alpha op times a factor, which is square root 2 log n over k, whereas the best known polytime algorithm gets only 4 over 3 times same factor. And there's a gap in between the two. And a work by David Gamarnik and Quan Lee from 2016 showed that this model exhibits something called overlap gap property, which I will tell you more about. As a result, some algorithms are going to break down for this model. Not all algorithms, but there is some evidence of hardness. So here is the state of affairs, at least at the time we were writing this paper. There were no rigorous results available for the tensors, where there are some now, which I will also mention. As for the matrices, the rigorous results, almost all of them are under the assumption that k is big O of log n. And Shankar Bhamidi, Parthade, and Andrew Noble actually explicitly highlight this regime when k is theta of n as an open question, and they say it will probably require more advanced techniques. So here is going to be the setup. As I said, k will be growing, but I'll just assume that k over n remains bounded away from 1 for some technical reasons. The most important thing, I guess, in this talk is that we'll be focusing on the regime not only n tends to infinity, but p remains large. So if you're familiar with line of work such as random k-sat or sparse random graphs, this is really a double limit where n tending to infinity is followed by p tending to infinity. And this will be the key quantity, which I will denote as Emax. It's a combinatorial quantity, and I will explain in a bit where it comes from. So here is the first result. Basically, we show that for large P, the ground state concentrates around this value Emax. So for any fixed epsilon, there's a P that depends on this epsilon such that whenever you fix any P, so you fix P first, and then you let n tending to infinity limit, the ground state concentrates around that value with this probability. So I don't think I will have much time to tell you about the proof, but if there is time left at the end, I will try to. The proof is a rather involved second moment argument. Basically, the second moment itself doesn't pin down this value. It gives you something with an exponential small probability, if you're familiar with how second moment method is used. So we basically repair this by using some insights from spin glasses, which are very recent insights. What do I mean? Basically, this M star, we interpret this as a supremum of a certain Gaussian process, which has concentration thanks to Borel-Tis inequality. And there's an argument of Fries in the random graph literature using these two ingredients, you can actually repair second moment. So we'll see if I have time to tell you about this at the end. So here's a bit more on the intuition, especially where this funny Emax come from. So recall the very classical probability 101 fact. If I have a bunch of IID Gaussians, then their maximum is their standard deviation times square root 2 log n. N is the number of Gaussians I'm looking at. So if we go back to this model here, this is really n choose k to the power p Gaussians, each with variance 1 over k to the p. So if you do the math, this is basically the value you predict, and it turns out this is the correct value. Just one word, where this comes from? Well, the tensors as p grows, they exhibit correlation decay, but I won't get more into that. So this is also what physicists would call, I guess, a multipartite Boolean spin class with Boolean spins, not Ising spins. But there's a sparsity constraint because I'm taking along each mode only k directions as opposed to all n. So there's a recent line of work by Ahmet, Andre, and Mark Selke, as well as David Gamarnik, Okosh Jagannath, and myself, which is mainly on shattering phenomenon in these models, which show that even though these are difficult for fixed p, they become actually far more tractable for large p. You can basically get some augmented second moment arguments to get pretty sharp results. And this seems to be the case here as well. Now I'll switch gear to the algorithms. And before I tell you our algorithm, I would like to tell you sort of the best known algorithm for the submatrix case. This is due to David Gamarnik and Quan Li. It's a really simple greedy algorithm, and it goes as follows. So we want to construct a k by k submatrix, start with an arbitrary row, find the maximum entry on that row, and then take that column where that maximum entry is located. Now, in this column that you picked, find the second largest entry. That will give you 2 rows. Once you have these 2 rows, find the column that the intersection with these 2 selected rows is as large as possible in the sum. And you repeat. So at any step, you have now 3 rows that are already constructed. Find the third column by finding, literally greedily, whichever column maximizes the sum, and you iterate until you have k in each dimension. So believe it or not, this is basically the best known algorithm, and there's a recent work which shows that this is the best we can do, and there is a good evidence that we may not be able to improve upon this. Okay, so this is the pseudo code, but I will just skip over and I'll tell one thing. How we extend this, it's pretty simple. Once you initialize all but one mode randomly, what you do is at each step, you focus on one of the modes. Whatever you have constructed so far, you try to find an index along that mode that will maximize the sum. And then as long as each direction reaches k coordinates, you basically stop and then you return those indices. So here's the result. Let this I hat be the output of this algorithm on the random input. Then we try probability as n grows. So here are the probabilities with respect to this random input. The output of this algorithm is actually 2 square root p over p plus 1 approximation for the maximum, as long as k is some polylogarithmic factor. So for this value, the algorithm reaches theta p 1 over root p max. And so I'll tell you in a second more about this work. Actually, if you don't want a big theta guarantee, but if you want a big O guarantee, you can actually push this all the way to sublinear values. So this model now has a computational gap. Optimal value is at E max, whereas the algorithms only get 2 root p over p plus 1 times E max. So we studied this by using something called multi-OGP, which I will tell you more in the next slide, which is a geometric barrier. And we showed that for any gamma positive, there's a sufficiently large p such that the model exhibits multi-OGP at this threshold. So asymptotically, the algorithmic threshold for this model basically reaches to 0. This is really analogous to random energy model, which is the p tending to infinity limit for these spin glasses. So here the threshold is asymptotically sharp in the sense that as p grows, both the onset of the algorithmic barrier as well as the algorithmic threshold reach to 0. But there is this follow-up work, really beautiful work by Shankar, David, and Shuyang. They show that the onset of branching OGP, which was originally introduced in the context of spin glasses, actually is precisely 2 root p over p plus 1. So this algorithm is likely optimal, and there's a strong belief we may not be able to improve this. I want to say some future works in case you're interested in. So fixed p, that my colleagues in the statistics community, they are really interested in this. So everything uses this large p and correlation decay. Fixed p is something I don't know how to do, as well as algorithms when k is theta. So here you're genuinely in the spin glass regime. So that's all for this one.
I assume that the entries are IID Gaussian.
IID
right?
Gaussian, yeah.
So
That's
if they're independent but not Gaussian, is it much different?
so good. This is something that the techniques are very Gaussian specific. I don't know how to do, and this is in fact in the work of Bamidi Day Nobel paper as well. The hardness should certainly be there. The algorithm should certainly be pretty much the same value. It's just that the techniques are specialized to Gaussian. Yeah.
In the interest of time, let's go ahead and introduce the next speaker and move on. So now Eren is going to tell us about planted random number partitioning problem.
Yeah. Okay. Thank you, Matush, again. So this talk would be about the planted variant of number partitioning. But before I present you the main results, I want to just tell you a few important points about this model so that we can appreciate it a bit. It's a model is very simple. It's given an array of numbers. I want to find the partition which is as balanced as possible. So any partition you can encode into a binary -1 + 1 vector in a binary cube. So you want to minimize this inner product. So this is a canonical problem in CS. Is one of actually Karp's 21 NP complete problems. And there is a paper by Tom Rothwusch and Becca Hobart. They show approximation is as hard as Minkowski and shortest vector. It's also an instance of discrepancy minimization. In statistical physicists, conjecture it exhibits very curious phase transitions, which this beautiful paper by Borg, Chayes-Pittel, and Mertens confirmed. And they are also quite curiously, recently it's been seen that they are linked to the design of randomized controlled trials. It's a paper by Dan Spielman's group. I certainly recommend taking a look at it. So as for the talk has 2 names, the planted number partitioning. As for the planted part, so planted models are literally bread and butter in modern statistics. You have a signal that's buried in random noise, and you want to recover the signal. The models such as stochastic block model, infamous planted clique, sparse PCA, they all have planted structure. They're also instrumental in studying especially solution space geometry as a probabilistic proof technique for the random constraint satisfaction problems, such as KSAT. So this talk again will be an average case talk where I will now delve into this gap more. Whenever the input is IID standard normal, this model exhibits an even dramatic computational gap. The optimal value is order 2 to the -n, whereas the best algorithm we know, which is due to Ben Yecker from '96, gets only n to the -log n. And we don't know anything better than this. So couple relatively recent hardness results. Even though this is an old model, the results are actually quite new. David Kamarnik and myself, as well as Rusil Malarapo and Mark Selke, all of us gave some unconditional lower bounds using multi-OGP. There is also a very nice recent paper by Wafa and Vaikunathan, where assuming worst case hardness of shortest vector problem, they actually give pretty much quite sharp lower bounds as well. So this talk will also get into this multi-OGP that I sort of hinted in the previous talk a little bit. This is a tool to link basically intricate geometry, the landscape geometry, to rigorous algorithmic hardness. And it has been quite successful in a host of random optimization problems that are unplanted. But for the planted models that are quite interesting in statistics, the existing technology only basically rules out either MCMC or simple local search. And more importantly, we don't have this multi-OGP machinery, which has been really the tool to saturate computational thresholds. So one goal in this paper that I had in mind was to show some of the insights from the unplanted models can be useful in the planted models, and I will sort of outline some future directions towards the end. Okay, without further ado, here is the model. We fix a partition sigma star, assume that's unknown, and we basically plant it in the following way. We sample X, that's conditional on the fact that the sigma star achieves a small discrepancy. So the value I pick here is 3 to the minus n. You can put there any constant that's as long as it's bigger than 2. So the optimal value under the random model, unplanted model, was 2 to the minus n. So this is statistically distinguishable. That's one thing to keep in mind. And throughout the remainder, I will refer to this object as the Hamiltonian. This is a classic notation in physics. So a bunch of questions you may ask is, now this becomes, you can talk about more recovering the planted partition. You can also talk about how can I optimize the Hamiltonian. So I'll focus on the former, whereas the recovery and hypothesis testing, I'll leave them as some future directions. And I'll tell you landscape results as well as geometric barriers. But this talk won't have positive guarantees. Everything will be lower bound. So here's the first result. All guarantees throughout would be under the planted measure. It turns out that the planting doesn't actually induce partitions with Hamiltonian substantially smaller than 2 to the minus n. So if you look at the Hamiltonian, that's other than the plus minus sigma star, you can see from the symmetry both get 3 to the minus n. Modulo some lower order factors, I still get 2 to the n as the ground state, which is little interesting because if you contrast this to, say, planted clique, if you plant a clique size a bit larger than log n to gn1/2, you automatically induce cliques of smaller sizes. So even though this is a local operation, it has an impact over the global structure, whereas planting does look like, at least at first glance, it seems like a global operation. It doesn't seem to impact the global landscape by much. So the proof of the previous result, which sort of reveals an entropy energy trade-off, which tells us that this is kind of intuitive, but the smallest Hamiltonian is actually achieved farthest from sigma, basically in midway between sigma star and minus sigma star. So here's a way to probe this landscape in more detail. Basically, if you fix any rho and look at the distances that are rho n from the planted solution, the smallest Hamiltonian that you can achieve is actually 2 to the minus n times binary entropy of rho. So this gives us basically as a function of distance the profile in a fairly precise way. And this zeta is the optimal value function of rho. You can see that zeta rho and zeta 1 minus rho are the same. And this makes sense because my distance to sigma star and minus sigma star, they sum to n. And from the symmetry, I could have planted sigma star, minus sigma is pretty much the same thing. So this makes sense that this has the symmetry in this way. There is one last result before I move on to the algorithmic hardness results. In fact, actually more is true, not only linear levels, but even if you take for any E that grows at least big omega of log n, there is a distance such that if you look at the vicinity of planted solution sigma star, then the smallest Hamiltonian is at least 2 to the minus. So this means that the landscape is kind of arranged in a hierarchic way. There is the sigma star and minus sigma star, which has the lowest energy. There are everything else that have intermediate energy, and then they are separated with sort of steep barriers. This basically in line of some prior work from late 2000s suggests that the solution is isolated, so recovery is likely computationally hard. But I don't know a proof of this, or at least even a rigorous evidence that this is the case, and will be an interesting future direction. So now I've been hinting this OGP quite a lot. Here is going to be a slide where I would like to tell a bit. These models are all average case models, so we really don't have an MP hardness type of technology. What we can do is we can, at least one approach is you rule out unconditional lower bounds against some classes of algorithms. And one of which was successful, at least for optimization problems, was the overlap gap property. So here is Here is how this property looks like. I will skip, in the interest of saving time, I will skip the rigorous definition. Basically, this model exhibits symmetric multi-OGP at an energy level if there is some m and a distance that depend on this level such that at this distance you can't find m tuples, all of which has this value and they are nearly equidistant. So these look like stars, and it says, this property says that this constellation of stars do not exist to begin with. And whenever this exists by some Ramsey theoretic argument, you can actually show that the algorithms that have certain stability properties necessarily fail for this model. So for this is a result which I suspect it's not tight, but one can show the multi-OGP for linear energy levels where m scales 1 over epsilon as a function of epsilon. And so for the unplanted case, the prior work by David and myself, we could show that this unplanted variant exhibits multi-OGP at 2 to the minus root n. Here, because the model is planted, there are a few technical hurdles which didn't overcome in this model, but it could certainly be interesting to push it there, and I think it's probably the case that that's the threshold for this. So the last result is the algorithmic hardness result, where we look at randomized algorithms that have stability and certain anti-concentration property, where stability, we've seen a lot of talks yesterday on differential privacy. So stability is a bit more general notion. If two inputs are small in whatever the distance is in the ambient space, then the outputs are small with some probabilistic guarantee. So this result shows that the stable algorithms that have a certain anti-concentration property actually fail to reach sublinear exponents. And this anti-concentration simply refers that your algorithm doesn't concentrate on the planted partition by too much. So if you were to run any optimization algorithm, it's not recovery, but let's say you were to optimize this. So this makes sense that reasonable algorithms satisfy this condition. I guess that's all. Yeah.
We have time for one question, and if the next speaker could go ahead and take over the screen share. Yeah, Lev.
So I forgot. So I forgot the name of the property that
Overlap gap.
Yeah, overlap gap. So
yes.
so is the lower bound directly from the overlap gap property? So this is the step I missed.
Correct. Yes. Directly from.
So there's just some theorem that
So-
you didn't prove that says if you have this, then you get a lower, like that step I don't.
So that's like, okay, whenever you first prove the overlap gap property, and then once you prove that property, there is a way to show that rules out algorithms. That you have to adapt the argument to the problem, but there is sort of a canonical way of showing that, yeah.
Because you could probably devise a problem where it doesn't induce a lower bound against an algorithm.
So
right?
no, actually, for all the problems we know, whenever there is, I guess, with an exception of one problem, which is, you want to solve the system of linear equations with which Gaussian elimination succeeds.
Yeah.
In all the problems we know, OGP actually does imply hardness of stable algorithms. So basically, the algorithm I can take it more offline, but in a high level, if an algorithm exists, you can run it on correlated instances, and you can actually extract the very structure that this property tells doesn't exist. That gives you a contradiction.
I'll bug you offline.
Yeah, absolutely.
Okay, let's thank Eren once again. Okay, so the next talk will be by Tanmay Devale on uniform convergence beyond Glivenko-Cantelli.
So good afternoon. I'm Tanmay Devale, and I'll be talking about our work titled Uniform Convergence Beyond Glivenko-Cantelli with Pramith Devulapalli and our advisor Steve Hanneke. So for binary function classes, we know that if VC dimension is finite, then we can guarantee uniform convergence independent of the underlying distribution. But uniform convergence can still hold for certain concept classes with infinite VC dimension for certain specific distributions. For instance, we consider the Glivenko-Cantelli property, in which when we sample n data points from some distribution P, the supremum over your concept class of the empirical mean minus the true mean goes to 0 asymptotically. When this occurs, we say that we have P Glivenko-Cantelli. In this work, we restrict ourselves towards countable function classes, and then any distribution on your data can be passed through your function class and can be interpreted as a distribution mu on 0, 1 to the naturals. So as an effect, your Glivenko-Cantelli property can be interpreted as an infinity norm between the empirical mean and the true mean, where the jth coordinate in that Q is equivalent to the output of the jth function. And the goal of this work is to find conditions on your distribution so that we can guarantee mean estimation. So if you have a collection of distribution with just one vector, which is a product distribution, and the mean is all 1/2, in this case, empirical mean estimator fails, because for every coordinate, there is a non-zero probability of observing all zeros or all ones, and you have infinitely many such chances, so it will almost surely occur. So the L infinity distance becomes 1/2. So this becomes non-learnable by empirical mean, but it's very easily learnable because there is only one possibility, so you can just return that. So in this work, we characterize collections of distributions over 0, 1 to the naturals, where we can estimate the mean using any estimator. So we define this new idea called uniform mean estimation or UME learnability, in which we say a collection of distributions is UME learnable by some algorithm A if for any distribution the algorithm returns an estimate Q tilde using NIID samples such that the expectation of the L infinity norm between the estimate and the true mean goes to 0 asymptotically. And as a reminder, we consider any arbitrary estimator other than the empirical mean estimator. So the two main results I'll be talking in this talk, presenting in this talk, is to show that if my mean vectors of my collection of distributions are separable, then it is UME learnable, and also that UME learnability is closed under countable unions. So by separability, we mean that for every epsilon, there exists a countable epsilon cover of mean vectors under the L infinity norm. So we say that we can show that for a collection of distribution, if there exists a countable epsilon cover, then there exists an algorithm which returns an estimate Q tilde such that for any mean, any distribution in your collection, there exists an N0, and this N0 depends on your distribution, such that for all n greater than N0, so if I have more samples than N0, then I can obtain an epsilon approximation. So I'll just give a proof sketch. So let this be the cover of my mean Q, and let Qi star epsilon be the vector in your cover which approximates Q star, and it's the first vector. And by Hoffeding, we know that for each and every coordinate with high probability, the empirical mean and the true mean are within root 3 log n over n. And as we have epsilon approximations, we allow an epsilon slack. And therefore, we develop a test in which we check for the first n coordinates if the deviation is around root 3 log n over n plus some epsilon. And note that Qi star epsilon satisfies this test. And our algorithm is really simple. We basically look at the cover and enumerate through it, and we return the first vector which satisfies the test. And Qi star epsilon satisfies the test with high probability. And note that there are only finitely many vectors which appear before Qi star epsilon. So for sufficiently large number of samples, the deviation is large for each vector appearing before Qi star at least one coordinate. So it will fail because of at least one coordinate. So we choose N0 such that that occurs. And note that we just show the existence of N0. We don't know what exactly N0 is, but it will find Q star asymptotically. Now we use those previous approximations to find what exactly Q0 is, Q star is. So what we do is we run our previous algorithm for countably many resolutions and look at the L infinity balls around the vectors that were returned by the previous algorithm, and let capital K be the largest value such that we can guarantee for every little k less than capital K, we have an epsilon k approximation. Your Q star, the true mean vector, will lie in all that intersection because it had converged. but we don't know exactly what k is. So we keep running the algorithm till the last non-empty intersection and choose an estimate in that particular intersection. So now these two vectors are going to be at most 2 epsilon k close together. And now note that if we let k go to infinity, n go to infinity, then k also goes to infinity. And as a result, we get what the true underlying mean is. We also show that UME learnability is closed under countable unions. So let Qi be learnable by AI using some estimator tilde Q tilde I. Let Q star be the true underlying mean. It belongs to some Qi star and it is learnable by some Q tilde I star. So our main task now is, so our idea is similar to what we had done earlier. We find an epsilon approximation and then we combine those epsilon approximations to find the true mean vector. The idea over here is to run a tournament. So we consider the first n estimates written by the first n algorithms, and we take one of them and compare and run a tournament against all the others. So I'll show a run of one of those tests. So let Q tilde T be the estimate I'm testing against the first n estimates. So if their L infinity normal is less than 4 epsilon, there is no way to differentiate between them. So we just move on to the next vector. So if it is more than 4 epsilon, there exists one coordinate where it is more than 4 epsilon. And now if my Q tilde T is closer to the empirical mean, then we say that, okay, Q tilde T actually passed the test. And now if it succeeds against all of those first n coordinates, then we say that, okay, Q tilde T actually succeeded across all of them. And it passed the survival test. Note that Q tilde I star wins this tournament. And therefore, as a result, we get a 5 epsilon approximation. And then we can use our previous technique to find the true mean vector. So unfortunately, separability is not necessary. If you consider the mean vectors to being binary, then as soon as you get one sample, you know exactly what the underlying distribution is. But this is a non-separable collection. But it is not. Exists another collection of product distributions with means in 1/3, 2/3 of the naturals, which is non-separable as well as not UME learnable. Therefore, non-separable paradigm is of independent interest. Some extensions that we have come up with is showing that the countable function class assumption is actually not needed. We can have uncountable function classes and separability is still sufficient. The reason we don't have that in our paper is because we found it 1 week before the deadline, so it's not the main paper. Then we can also show, and if you remember the proofs that we had, we fix the distribution and then let n go to infinity. So it's not uniform over our collection, but we can also show certain bounds which are uniform over the collection as well as which are uniform over the concept class as well as the collection of distributions. But for that we need the collection of distribution to be totally bounded. That is, the epsilon covers needs to be finite for every epsilon under the infinity norm. So so we have shown that separability is sufficient, but it's not necessary. So are there any concise necessary and sufficient condition when we do not restrict to our mean vectors to be separable? And can we provide complete characterization of optimal UME, optimal uniform and universal rates of UME learnability? Thank you.
Okay, we have time for questions, and as usual, if the next speaker could kick off the current screen share. Give us your personal favorite example of a function class which is UME learnable and not Glivenko-Cantelli.
There is, you need beer to understand it. It's hard. Yeah, it's hard to explain it. It's like a tree, and so you take a tree and you label certain branches, and it's non-separable and it still remains learnable. It's a very weird example. I can tell you that offline. Yeah.
Yeah. Luckily, we all had beer at lunch, so we all understood that. Let's thank the speaker again, and if the next speaker could come up.
So my name is Akshay Ramachandran, and today I'm going to talk about optimal bounds for Tyler's M-Estimator for elliptical distributions. This is joint work with my PhD advisor and co-author, Lapti Lau, who's at Waterloo. Cool. That's the outline of the talk. I'll give some background. It's a pretty simple to explain statistical problem. There's been some previous work, and then I'll state my main results. And then if there is time, I will describe some proof techniques and some future directions, which I think the proof techniques are of independent interest. The technical improvement quantitatively is a little small, even though it's optimal, but the proof techniques, I believe, would give new results in a bunch of places. Cool. So the background, we start with maybe the most basic statistical estimation problem. So we're given centered Gaussian distribution and samples from the centered Gaussian distribution. And then the thing we want to estimate is the covariance matrix, right? So the most basic problem. And this is in some sense like the gold standard problem for these reasons. There's a very simple answer to this question of the sample covariance. It's very easy to compute. In some sense, it's optimal. In what sense, I will not exactly talk about at the moment, but you reach this optimal sample complexity. And why is this optimal? In one sense, you need at least dimension many samples to see the whole space. And as soon as you get more than dimension many samples, you get a good approximation for the true covariance. Throughout, I'm going to be using this very vague notation of squiggly epsilon. There are some subtleties about how you define approximation that are actually pretty crucial to why our result is as good as it is. But I only have 10 minutes, so please ask me after the talk. Yeah, but this is the gold standard that we should keep in mind, and it's optimal both in terms of epsilon and in terms of the sample threshold. So as soon as you get more than D samples, you start getting actually an approximation. So that's what we'd be aiming for. And this is the most basic version of the problem. Let's generalize it a little bit to a very simple to explain model, but actually a pretty expressive model. So first I'm going to draw a cartoon for fun. So elliptical distributions you can think of as spherically symmetric after doing a linear transform. So these ellipsoids represent, let's say, level sets of the PDF. And so after doing a linear transform that is controlled by the shape of the ellipse, then it looks spherically symmetric. For example, the Gaussian is one of these, right? But it's a useful expressive model because it actually captures a lot of heavy-tailed data, heavy-tailed distributions. So of course, the Gaussian is an example. So is like the uniform distribution over a sphere, but so is this like student T distribution. And so heavy-tailed in the sense that actually the covariance matrix of that last distribution doesn't exist. So it is infinite variance. And yet we can try to estimate some nice properties of this distribution. So what do I mean by this distribution more formally? I think you don't have to worry so much about the formal definition, but it's enough to keep this picture in mind. An elliptical distribution is defined by two parameters. One is the shape matrix, sigma, and the other is this norm random variable. And formally, the direction of your random vector after this normalization and the norm of your random vector after this normalization are independent. So they're independent random variables. The direction does not depend on the norm. And this part is spherically symmetric. So after doing the normalization by the shape matrix, it's spherically symmetric. Cool. Any questions on the model so far? So these models could have unbounded variance, but we still want to learn something about them. And in particular, what is the estimation problem? We want to learn the shape matrix. We don't care about the norm random variable for this talk. So that we consider as a nuisance parameter, and we want to learn the shape matrix in the same way as learning the covariance matrix of the Gaussian. I will actually say one more thing. In the setting where the covariance matrix does exist, the shape matrix matches that up to a scalar. This is a meaningful generalization. Cool. And I won't leave you hanging so much. The punchline is we match the sample complexity guarantees of the Gaussian for this much broader class of distributions. We don't, so we analyze a known, very well-studied estimator called Tyler's M-Estimator, and we show it achieves optimal sample complexity that matches the Gaussian. Yeah, so yay. Cool. So I will discuss a little bit of the timeline about what the previous results were, and then hopefully we'll get to proof techniques. But any questions on the model and the results? All good. Yeah. It's a relative spectral norm, but definitely please ask me after. It's an awesome. Yeah. Yeah, it is like the tightest guarantee you could hope for that is statistically meaningful, I would say. Cool. So here's a very abridged timeline. The seminal result in this class of distributions was by Tyler in '87, where he studied this class and he defined the estimator that we're going to define in the next couple of slides. And he proves some really beautiful results. So he defined the estimator, he defined a nice procedure that converges to this estimator, and he proved asymptotically that this achieves the optimal rate of error, and also that asymptotically this procedure that he defined converges to the estimator. And he proved that it's all these guarantees are distribution independent, meaning I don't even tell you which elliptical distribution it is. I don't tell you what the shape matrix it is. In some sense, like this is all agnostic, and you get uniform bounds for all of them. And these are best possible because these even match the Gaussian setting. So this is what we wanted to match for a long time, but notice these are only asymptotic rates. So in 2014, Soloveichik and Weisel, they gave the first non-asymptotic bounds, but these are distribution dependent. So we lose this like really nice uniform property that doesn't care about which distribution. And they analyze Tyler's estimator, but they're not able to analyze the iterative procedure. So it's not clear actually how to build an algorithm to compute the estimator. And so the next really nice result in this line, which is I think where I like entered the question, was by Franks and Moitra in 2020. And so they gave these near optimal sample complexity bounds that are importantly distribution independent. And another really nice result is that they were able to prove that the natural iterative procedure that Tyler defined converges linearly to the M-Estimator. So these are, like, I would say, pretty surprising results. There was a really nice connection to what's called geodesic convexity, which, again, I will not talk about too much in this talk, but ask me after. And this was a real key to understanding, like, both the algorithm and how to analyze the estimator. Cool. And so the final box in this line is our result. So we improve on this previous result to remove the near from the near optimal, and we give optimal sample complexity bounds. Importantly, we do a little bit more work than just using G-convexity. We have to use a little bit more structural assumptions about elliptical distributions. Cool. And so I will repeat the main result just for clarity. So Tyler's M-Estimator, which was defined, achieves optimal sample complexity bounds, meaning as soon as you have n more than d many samples, you get this epsilon rate of error, of course, with high probability, sorry. And at the same n bigger than d many samples regime, the iterative procedure converges linearly to the estimator. Cool. So as soon as you have enough samples to even see the whole space and like figure out what all the entries of the matrix are, you get this nice linear convergence to the estimator. Cool. Yeah, matches the Gaussian lower bound. It improves on the previous work by a few log factors. I'm okay with this for two reasons. One is it's optimal, so you can't improve anymore. And two is I think the technical results we prove are quite nice and of independent interest. So yeah, cool. So now if we have 2 minutes, I will give a little bit of proof techniques. So I haven't defined for the estimator. This is the first time. So this is a equation satisfied by the estimator. So sigma is the shape matrix. Sigma hat is the solution to this equation. Okay, and let me give you some intuition. The elliptical distribution after you normalize becomes spherically symmetric. And so you'd expect the covariance of the normalized thing to be the shape matrix. So that's sort of what it's doing. So you divide by the norm, and then you compute the normalized covariance, and you'd hope it matches the thing that you guessed. Cool. And importantly, by pretty standard matrix concentration inequalities, the true shape matrix approximately satisfies this equation. Cool. So our goal is, this is the estimator. We want to show the true solution to this equation matches the true shape matrix, which approximately satisfies the equation. And so now the key here was, this is the approach of Franks and Moitra, is you connect to this problem called frame scaling in theoretical computer science. Maybe I'll speed up a little, but I just want you to notice sort of the similarity in formulas. And so the idea is, if you connect to this problem, you can use analysis from scaling to analyze Tyler's M-Estimator. So Tyler's M-Estimator is the solution to a particular scaling problem. And scaling you can analyze using this thing called geodesic convexity. And better yet, elliptical distributions produce instances that are strongly geodesically convex. So this is the main contribution of Franks and Moitra. So you can actually give strong quantitative bounds. You can use scaling analyses for strong convex instances to give strong quantitative bounds on Tyler's M-Estimator. Cool. So we're going to build on this approach and just improve a couple places to give the final log factors. So our strategy, we define another notion of convergence, which is an operator norm analog of strong convexity. It's not so important what the formula is. But we use this operator norm analog to give the tightest possible bounds, which gives our optimal sample convexity. And so let me just flash the two technical results, which I think are of independent interest. So we show that we give a new analysis of scaling under this operator norm analog of strong convexity, which gives even tighter bounds on the scaling solution, which we can then use to analyze Tyler's M-Estimator. And we show that the elliptical distribution instances are not only strongly convex, but this like stronger notion of strong convexity, known as infinity expansion. So, and this is all at the optimal sample threshold. Cool. So this is like where we gain our log factors. Cool. So in conclusion, we gave a new notion of convergence. We did an analysis of scaling, which was used to analyze Tyler's M-Estimator, and we showed the elliptical distributions satisfy this new condition, which led to optimal guarantees. And then if I have 30 seconds, I will say some nice future directions. So there's a bunch of structural assumptions you can incorporate to get better sample complexity bounds. This is for the general elliptical case. Maybe you have more structural assumptions so you can hope for better. The other two nice problems that I've been thinking about, there's a nice problem called Paulson problem in operator theory, which used similar techniques of scaling. And we'd hope to use infinity expansion to give optimal bounds there. And also another problem in statistics called the tensor normal model, which similar techniques, so we'd hope to improve there. Cool. That's all.
So we'll take one quick question. Also, I want to say I completely spaced on introducing the speakers. This is Akshay Ramachandran. So yeah, I don't know how that happened.
Are these results in expectation or with high probability? And if with high probability, what's the delta dependence?
With high probability and log 1 over delta.
Less or time or what?
Sorry, what happened? For the relative error, I think times, but I can check.
Okay, let's thank the speaker again. Okay, so our next speaker, I'm remembering to introduce, it's Maxim Raginsky from IUC, and he's going to tell us about Gaussian process upper and lower bounds if you replace the supremum with a log sum x.
Okay, great, thanks. All right, I know mine's the last talk, and I asked Yifeng, who's my PhD student. He's close to graduating and he's looking for a postdoc right now. He's absolutely amazing, but he couldn't be here because he'd have ESA issues. Anyway, so the title has the phrase Talagrand meets Talagrand, and I'll explain what that means. If you look at Gaussian processes, so we have a centered Gaussian process on some index set, and we're going to endow that index set with a canonical metric given by the covariance structure of the process. You can look at expected suprema, expected maxima, and for that we know, for example, upper and lower bounds given by maximal inequalities. For the upper bound, delta is the diameter of the metric space, and the lower bound given by the Sudakov minoration. Alpha A is the minimum separation between any two elements of the process. And of course, you can use chaining to do a more refined analysis, multi-scale analysis. Now, it is often interesting to replace the maximum with a softmax. And there are various versions of softmax. For example, you can use something called quenched free energy. So you compute the partition function, which is just this sum of exponentiated values of beta xt. Beta here is the inverse temperature, and you compute 1 over beta expected log of that. And this satisfies double-sided bounds that allow you to replace it with the maximum as beta goes to infinity. So temperature gets cranked down to 0. Or you can have the quenched Gibbs average. So the idea here is that you associate with each t a random probability, right? Because xt is random. So the probability is proportional to e to the beta xt. And then you compute the average value of xt, and then you take the expectation over the randomness of the Gaussian process. And this, by the way, explains the term quenched. So in statistical physics, these would be instances of what's called disordered systems, where you have a system with some energy function. The configurations are elements of t. The energy function itself was random. And quenching means that we first do all the statistical physics for a fixed realization of this randomness. And then we take the expectation with respect to that randomness at the end. And so Talagrand meets Talagrand refers to the fact that the first bullet is in, let's say, Talagrand's book, Upper and Lower Bounds for Stochastic Processes. And the second bullet is in Talagrand's 2-volume book on mean field models for spin glasses. As far as I know, he never really wrote anything connecting the two, so we're trying to do this here. So here are the main results. So we're considering T to be a finite set. And as I said, we can define this Gibbs measure. It's a random probability measure on the index space. And we're going to show upper and lower bounds on both of these quantities that I defined in the previous slide, the quenched Gibbs energy and the quenched quenched Gibbs average and free energy. And the bounds look like this. The upper bounds would have square root of the expected value of a divergence between the Gibbs measure at inverse temperature beta and Gibbs measure at inverse temperature 0, which is just a uniform distribution on T. So we have here the Kullback-Leibler divergence for the Gibbs average and Rényi half divergence for the free energy. And we actually have lower bounds that match this. So for correlated Gaussian processes, there's going to be a critical inverse temperature. So for low temperatures, we actually have something like a Sudakov type bound. But when the elements of XT are IID, this holds for all the temperatures. And for IID, we also have a lower bound with the Rényi half divergence. Now, and this is actually extremely simple, but the nice thing is that when you take beta to infinity, you recover log cardinality of T. And you kind of want that. So this expected divergence is a proxy for log cardinality of the set. Here's the upper bound. So the upper bound actually can be extended easily to sub-Gaussian processes. So if XT is sigma sub-Gaussian process, then for any beta, we have this upper bound. In fact, here we can identify the constant, that's square root of 2. And because this relative entropy is actually the difference of two Shannon entropies, so log T is the Shannon entropy of the uniform distribution, and whatever Shannon entropy you get for the Gibbs, when you take beta to infinity, so 0 temperature limit, you actually recover the upper bound with the correct constant. And the proof is actually a very simple consequence of the Gibbs variational principle that tells you something for this log partition function. You just need to choose the energy appropriately, this function ft. It's going to be minus lambda xt, and then you tune lambda. So this inequality is Gibbs, and this inequality is just using the fact that your objects are sub-Gaussian, and you optimize over lambda. For the lower bound, we have the following theorem. So xt is a centered Gaussian process now, which has this minimum separation property. So any two distinct elements S and T are separated by at least A in this canonical metric, and there exists a critical value beta star for the inverse temperature such that for all beta larger than that, so this is a low temperature bound, the Gibbs, the quenched Gibbs average is lower bounded by the separation times the square root of the expected KL divergence. And if the random variables are actually IID Gaussian with variance sigma squared, then this holds for all the temperatures. And the constant here is proportional to the constant in the Sudakov minoration inequality. And this proof has a couple of ingredients. So first of all, we use this what's called the replica symmetric representation of quenched Gibbs average. This is a very simple derivation using Gaussian integration by parts. But notice it involves the square distance between any two elements S and T, and then the expected value of the corresponding probability product. And if you look at the sum of the squares of the probabilities, that's the squared L2 norm of this probability vector, this function is actually monotone in beta. Its expected value is called the participation ratio. That basically tells you, like, as these probabilities become more uniform, you end up with something that scales, I think, 1 over t. Anyway, so if you use the replica symmetric representation, you end up with a formula for g of beta that involves this expected value of this squared L2 norm. And when you're working in a high temperature regime, basically the idea is that this g of beta has distinct behavior for high and low temperatures. For high temperatures, it basically behaves quadratically. And then you can use some very simple inequalities to lower bound it like this. But then if you write out this value for the KL divergence, that is missing an expected value here, you get this lower bound. For the low temperature regime, the idea is to look at this gap. So this is the gap between the Gibbs average and the Sudakov type bound. And you can actually show that there exists a value beta star, which depends on the covariance structure of the process, such that when this function is monotone and you take beta to infinity and you end up with a Sudakov gap, which you know is non-negative. I'm not going to talk about the bounds for the quenched free energy with Rainy half that can be found in the paper. But the interesting thing is that, for example, we can get finite system size bounds for the random energy model. Random energy model is seemingly a very trivial object. You have basically IID Gaussian random variables sitting at the vertices of a Boolean cube of dimension n with appropriately tuned variances. And it's the simplest model of a disordered system because it actually exhibits a phase transition. As you take n to infinity, there's a temperature, critical temperature equal to twice squared log 2, such that above the critical temperature, the limiting value of this quenched pressure behaves quadratically in beta, but above the critical temperature, or below the critical temperature rather, it behaves linearly. And actually using all our bounds that we presented before, it's possible to obtain the following upper and lower bounds on this pressure for any finite n. Here beta star is the same critical temperature as in the Sudakov type lower bound. And here you just need to optimize over this elbow where the transition between linear and quadratic behavior happens. As I said, I mean, to derive these bounds, it really is just a straightforward application of the upper and lower bounds that we had for the IID case. And we're actually working on some interesting extensions. For example, we actually now are obtaining multi-scale chaining type bounds. And it's possible to go beyond finite index sets. So you do end up with something like a Fernique-Talagrand-like decomposition for the softmax. And I think that's all I have.
So we have time for a question.
Thank you for the talk. So I'm just curious. So it seems like replica symmetry was important in your improving your bounds.
Yeah.
Do you think any of the machinery can be reused for mean field models that have replica symmetry breaking? So like a Sherrington-Kirkpatrick model, or?
Yes. So it's not the same machinery, but the ongoing work that I have right now, we do in fact have finite n bounds for the Sherrington-Kirkpatrick model. The lower bound is where we can use our methods. The upper bound is just the usual Guérin interpolation method.
Okay.
Type bound. The key is to find the right order parameter for the Parisi equation, and we actually do have that.
Okay, thank you.
Sure.
Okay, just because if it's quick.
Okay, just one question: is this expected KL divergence typically easy to compute on some simple examples?
Is it easy to compute? No. Because I mean, you still end up with the random Gibbs measure. You need to compute its Shannon entropies, and that itself can exhibit phase transitions and other non-trivial behavior. So no, it's not easy to compute. Which is why the chaining expansion actually kind of replaces all that, and it works with certain saturated estimates for covering numbers.
So let's thank Max again.